second lecture of dynamics after that of Professor Colby, so that I will show you the theoretical part of dynamics of semidilute polymer solutions. So this is related to this first example of experiments. Okay, so what I will show you today, first part of this lecture, is the dynamics of semi-dilute polymer solutions, flexible polymers, so that it can be unentangled or entangled. So that this is dynamics, so that basically we study the relaxation times, relaxation modulus, and viscosity. And we know that the regime mode, Rouse mode, and repetition. So you have already a certain number of lectures from different professors, so that I try to summarize the relationship between that. For dynamics, Professor Colby has shown to you the Rouse and the Jim mode in dilute solutions, so that we will take the certain number of equations from here. Professor McLeish and Professor Rubinstein today talked about the repetition and the tube of the entanglement, so that I go further to study the concentration dependence of this repetition and the tube length. And for the static part, of course, Professor Grossberg and Professor Rubinstein has already talked about the chain size of real chain, and the correlation length has been already introduced. So that I'm going to show you how these lengths and these dynamics depends on the polymer concentration. So that already I'm talking about semi-dilute solutions, so that overlap concentration and the entanglement concentration should be here. Okay, so for dilute solutions, Professor Colby has shown many things, so that I just take the same equation. Just for as a reminder, chain size R is the product of the monomer size. This is Kuhn monomer size B, and N is the number of Kuhn monomer in a chain. It's the exponent of nu, the Flory exponent. And the Jim relaxation time is introduced, so that this is the diffusion of the chain at the length scale of its own size. So this Jim diffusion coefficient from the Einstein relation is given here, so that it's the function of R and the solvent viscosity eta S, so that it contains N here, so that in the end you can only use R here. Jim relaxation time is proportional to RQ. That's what you saw. And unentangled terminal modulus was also given, so you should know that modulus is basically the energy Curti per unit of volume. So here this is the volume occupied by a chain, so that this is in fact N over C. Just reminder, C is number concentration of monomer, so that we will convert it into the volume fraction phi at the next slide, so that this is the relationship between C and phi. Phi is over, C is phi over BQ. This is also already shown. Okay, so this means N over C, this is the concentration of one chain. And also polymer contribution to solution viscosity is given, so this is the solution viscosity eta minus solvent viscosity eta S is the product of modulus and the relaxation time. And then you have this relationship. So basically, that's what you have already learned. Okay, let's go to the semi-dilute solution. And already, as you know, an important length appears. So this is correlation length xi. So it is between monomer size B and chain size. And in this semi-dilute unentangled solution, at the length scale shorter than the correlation length, hydrodynamic interactions dominate the dynamics, so that you can describe the dynamics by the Jim model. However, at a longer length scale than the correlation length Guzai, hydrodynamic interactions are screened, okay, so that you can use the Rouse model to describe the dynamics. So basically, this is the simplest thing, and then we need to be carefully use Jim model or Rouse model to describe the different dynamics of the system. So the semi-dilute unentangled solution start from the overlap concentration phi star. So what is happening here, the coils of polymers start to overlap, start to touch, so that these coils of polymer are space-filling. So this is at the limit of dilute solution, so that we can still use the relation description of the chain size in dilute solutions, so that this is the same thing as you saw before. And then the space is filled by coils, so that the overlap concentration is equivalent to the volume occupied by Coulomb monomers in this chain. Okay, so that this is the volume of chain, and this is volume of Coulomb monomer and its number. Then this relation you have already, you know that before, so that this is phi star is n to the power of 1 minus 3 nu. Okay, so that size of chain is related to the overlap concentration. And then we can continue to increase the polymer concentration. At the concentration above the overlap concentration, you start to have the correlation length. So that's small schematics like that. So that at a given chain in red, you have correlation blobs of the size. Its size is Guzai correlation length. And you can still have, of course, the size of this chain. It is important that blobs also are also space-filling, so that the concentration of polymer can be, should be the same as the volume of monomers in one blob. Okay, so this is Guzai cube is the volume of blob, and then this is the volume of Coulomb monomer, and G is the number of monomer in a blob. Okay, so from this relation, we can have this relation. I think Professor Grossberg has shown already, so that Guzai is a function, is the product of B monomer size and the concentration dependent part, phi to nu over 3 nu minus 1. And then this is what is said, so that the G can be also the function of phi, so that we have this relation. And then the chain itself, this is in fact Gaussian chain of blob, so that this is the description by Rouse model, so that this is the size of chain, is the size of a monomeric unit. In this case, this is correlation blob. Its size is Guzai, and then this is the number of blob in a chain is a factor exponent of 1/2. Okay, so that we check carefully the phi dependence, and then in the end we have this relationship. Please remember that what Professor Grossberg showed you for the case of a good solvent, nu equal 3/5, phi dependence is minus 1/8. That's what you heard before. Okay, so I let you calculate the change here, so that this is very weak concentration dependence. Okay, and for my lecture, I follow the textbook of Professor Colby and Professor Rubinstein, so that I show the case from now on, two limits. So one is a thermal solvent case, and the other is a seat solvent case, so that the color is orange and purple. So that for the correlation length and the size of the chain, we can put for a thermal solvent, nu equal 0.588, and for theta solvent, nu equal 0.5 to have the dependence, concentration dependence of these lengths. Here, this is correlation length, and this is the size of the chain, so that this is very close to 1 minus 1 over 8. In fact, just a very small difference here. And Professor Grossberg also showed this types of diagram length as a function of concentration. For the case of a thermal solvent, at dilute solution, the size is constant, but once it starts to overlap, the chain shrinks. Here, this dependence is exponent is minus, negative, so that it slightly shrinks. And then from here, correlation length appears, and then it decreases also with the concentration. Theta solvent has stronger concentration dependence. Okay. Okay, so from here, this is it's a dynamics. We can calculate the relaxation time of a blob and that of a chain. So inside the blob, so that this is a Jim model, so that the description of the relaxation time is this Jim time, shown already by Professor Colby. So that what you need is the solvent viscosity and the size R. Here the size is the size of a blob, Guzai, so that we have this relationship. And we input this concentration dependence of Guzai. In my slide, what is written on the right in gray, this is the equation which had been already shown in our lecture or previous lectures, okay, just for reminder. Sorry. After that, for a chain, this is bigger than the correlation length, so that we can apply a Rouse model, so that the relaxation time of the Rouse mode is the product of the relaxation time of monomeric unit and its number square, so that we can use relaxation time of the blob here. And then this is the number of blobs, so that this is the number of monomers in a chain, and this is the number of monomers in a blob. So then just carefully change and check the exponent to have this relationship. Okay, so the relaxation time of the blob decreases with the exponent of minus 2.3, and in your theta solvent, exponent of minus 3, stronger dependence, and relaxation time of the chain. In your thermal solvent, this is exponent of 0.31, and in your theta solvent, it's 1. So this is the size of the system, so that here. So simply, if the length scale is shorter than the correlation length or not. Okay, the length scale shorter than the correlation length, or inside the blob, it's a Jim model.
Could you use the mic? Sorry. Could you use the microphone?
Ah, sorry. Yeah. Okay, so this here, this is the correlation length xi, and then at the length scale shorter than this length, then it's a Jim model. Okay, so that this is because hydrodynamic interaction is still there, but at length scale above the correlation length, hydrodynamic interactions are screened. Yep, exactly. With the interactions. So that yeah, so that here this is a chain. So this is in fact a blob. So that this chain is a Gaussian chain, in fact, of this blob. In this schematics, you have 5 monomers. Okay, so that this behaves that. But inside, in smaller length scale, it should be a gym. Okay. You're welcome. And here, okay, so then the chain relaxation time increases with the concentration. However, here this dependence is a little bit tricky. So if this nu for flexible polymers, no problem for that. But if nu is bigger than 2/3, then this dependence can be 0, and higher than that, it becomes negative. Okay, so that in the case of polyelectrolyte, chain is stretched so that this exponent becomes negative, so that relaxation time decreases. Okay, so that depending on the structure of the nature of the chain, this dependence can be different. But here I'm talking about flexible polymer and see the effect of the quality of solvent. Okay? It's okay? Okay, then the diffusion coefficient, so that the diffusion coefficient, this is the chain takes the time of chain relaxation time to diffuse at the length scale of its own size. So this is the definition. And then dependence of Earl and tau chain, it has been shown, so that just we input everything here to have this relationship. I let you check the calculation later. And then it is normal that there should be a limit at very dilute solution case, so that this is for diluted solution limit. So this should be the size of diluted polymer chain diffusion coefficient. And then with this, we can simplify the calculation. We can remove KT and eta S. And further, please remember that there is a relation between phi star and N with this, so that, in fact, we can replace this N-dependent part with phi star. So that this is very simple relation, and it seems logic, I think, so that diffusion coefficient is proportional to the that of a diluted solution, and then phi can be normalized with phi star. And then again, in a thermal solvent, D decreases with the concentration, and power law is minus 0.54, and for fit solvent, this is -1. So in the textbook of Professor Rubinstein and Professor Colby, you can have this example from the literature, and then at the dilute, semi-dilute solution and entangled, you can have roughly this slope of minus 0.54. At higher concentration in entangled regime, I will show you later. Okay. So this is stress relaxation modulus, and then as I will show you the result of microrheology, so this is a little bit important, so that this is the same scale in length and time also, so that you have 3 characteristic lengths: monomer size, correlation length, and chain size. And there is corresponding characteristic times also. And again, at length scale, smaller than the correlation length, Guzai, you can apply Jim model. So that this equation from the lecture of Professor Colby, so that this is Jim mode of stress relaxation modulus, so that is here exponent, you have nu. However, at longer length scale, longer than the Guzai, you can apply Rouse model, so that the form is similar, but exponent is minus 1/2. So then we can replace it with phi to have this relation. And then this is Rouse model, but this Rouse chain has blobs as monomers. And then its relaxation time is tau Guzai, so that B coming from C and this tau 0 can be replaced with those of blobs to have this relationship. Okay. Okay, let's check two extreme cases of each region, so that this Jim relaxation modulus works between monomer size and correlation length between tau 0 and tau Guzai. At T0, it's simple that you can eliminate this time-dependent part to have the modulus at the monomer level. Okay, so this is KT over B cube and phi. And the longest limit at correlation length, you can input tau Guzai here, and then after that, carefully check the exponent for phi. It's here 1 and here, and then to have this exponent. Okay, so that this is KT over B cube and phi to 3 nu divided by 3 nu minus 1. Or more simply, modulus is in fact energy KT per volume considered, so that the volume here of the correlation length is Guzai cube. Okay, so that simply KT over Guzai cube, it works to have the same relationship. Okay, so that I can calculate the limit cases for certain characteristic time. Okay, for the Rouse model part, above the correlation length, you can do the same thing. So gray one, this is for at the correlation length at T equal tau Guzai. You can input tau Guzai here simply, so that you can have exactly the same relation calculated previously. Okay, so these two equations matches at Guzai, it's normal. And then at the chain level, okay, when tau is tau chain, when T is tau chain, we can input tau chain here, and then we calculate concentration dependence and N dependence to have this relatively simple relation KT over B cube and phi over N. So this calculation is further simple if you take the modulus as energy KT per volume, and here the volume is the size of chain R, so that simply KT over R cube. And then in semidilute solution, chains are always space filling, so that phi is equivalent, the same as the volume occupied by monomer in the chain. Okay, so that we can use this relation to have this equation. Okay, so that we get the same thing. Okay. Okay, the stress relaxation modulus at further longer time scale above relaxation time of the chain. So that in that case, we can use the Rouse model with exponential cutoff. Professor Colby did that for dilute solution also. And for this case, the size of the chain is, this is the modulus for the, at T equal tau chain, as relaxation time, you can take tau chain and with the exponential cutoff. So that this is calculated curve from the textbook. So you can have, in fact, crossover of Jim mode and Rouse mode. Okay, the modulus is decreasing sorry, as a function of time, and until tau guzai, you are inside the blob, so that you have Jim mode. So that slope here is coming from Jim mode in a case of a thermal solvent. And after that, you have Rouse mode. So that slope is minus 0.5. And then you have relaxation of the chain cutoff, exponential cutoff. So that I will talk about this crossover from Jim to Rouse, but this is a very interesting question, and experimentally how we can do that. So this is one thing I want to show you during my lectures. Okay. The polymer contribution to viscosity, so that this is solution viscosity minus solvent viscosity. So this is polymer contribution. And then you can calculate with this integral of the stress relaxation. So this is controlled by the chain relaxation time to have this relationship at a longer time scale. You can calculate specific viscosity. So this means you can divide, you divide the polymer contribution to viscosity by solvent viscosity. And then you have the relationship here, n and phi 2 minus, not minus, 1 divided by 3 nu minus 1. Okay, so for the case of a thermal solvent, the exponent should be 1.3. And in a theta solvent, exponent is 2. So that you can see the example of polyethylene oxide in water showing the slope of 2. Okay, by the way, I have never seen this one. This, Professor Colby, you have the data reference for this exponent? I think so. So I searched, but I haven't to find it. So okay, so this is the, sorry, this is unentangled solution. I'm sorry. This is a summary of different properties at 3 different length scale, and this is relaxation time and the modulus at the given time and length, and then this is viscosity. And in between you have Jim relaxation modulus, Rouse relaxation modulus, and with exponential cutoff. Okay. Okay, so then we go to the semi-dilute entangled solutions. So the situation is getting more complex. So you have already taught that there is the tube diameter of entanglement in the polymer solutions and melt when it's entangled. So that this is the schematics. So that small circles, this is in fact correlation blobs. It's always space filling. And for a given chain here, emphasize here, this chain is, its movement is constrained, topologically constrained by the neighboring chain, so that it's like this chain is in a tube, its diameter is A. So that when you zoom in this tube diameter A, you have a chain, part of a chain. This is entanglement strand. This is a chain, Gaussian chain of these correlation blobs. So that let's study how this tube diameter A and the number of monomers in an entanglement strand, Ne, vary with the concentration. Okay? Okay, for entanglement, it would be helpful to start from melt, so phi equal 1. And for the chain size in the melt, so this is chain is random walk of monomers or random walk of entanglement strand. So the chain size is either with the monomer size B and its number N, or the size of entanglement strand and its size. And for the number, you have the exponent of 1/2. And this 1 in the parentheses means this is phi equal 1. So that you can calculate, you can see that A is proportional to B, it's the product of B and Ne to the power of 1/2. This relation has been shown this morning. So Ne is equal to A squared over B squared. And we can calculate also the chain tube length. So this is average primitive plus contour length, so that this is the chain length. So this is proportional to the size of the monomer inside, and then its number. So that it can be calculated as Bn divided by Ne to the power of 0.5. So this is shorter than the contour length of the chain itself. It should be Bn. So that this means the chain is a little bit compact in the entanglement tube. Okay, so that here you have this. It's not straight line. It's not fully stretched. Okay, how we can measure these lengths? It's possible to work on the melt of polymer with known monomer size and number, so that you know the chemistry of your chain. So that this is not Kuhn length, but real monomer size. And experimentally, we can reasonably measure the molecular weight, density of the melt, Plateau modulus of the melt, and by scattering, as Professor Brule showed this morning, you can measure the size of the polymer so that it can be end-to-end distance. This means you can calculate characteristic ratio. So this is the ratio, the end-to-end distance of your chain divided by NL squared. So this is the size if the chain is ideal. So real chain is not ideal, so that its size is bigger with this factor. Okay, so that this way you can calculate Kuhn length B with this characteristic ratio. And here, this is the bond length. Most of polymers are made of the chain of carbon or silicium, otherwise you don't have a very high molecular weight chain, so that it has 4 arms per atom, so that you have certain fixed angle. So this is phi, not phi, theta. It should be about 100 or something. I forgot the exact value. Okay, you can measure the entanglement molar mass of the chain, and you know the density. This R is gas constant, because this is the unit is mole, so that you can calculate this entanglement molar mass. It should give you the volume, entanglement or volume. So this is the occupied volume of an entanglement strand. You can measure this. And a chain in the melt, it's Gaussian, so that you know its size from scattering. So that this means chain of Rouse chain A in monomeric size and its number in the root. So that this way you can calculate tube diameter also in the melt. This allows you to calculate the number of monomers in an entanglement strand, NE, as you know already, B here. Okay, so that this is entanglement volume. In fact, it's already known, but this is related to the number of, volume of occupied volume by monomer, and then this is its number. And then this is important. You can have a confinement volume, AQ. This is the size of your tube. In fact, inside there is not only one chain. Okay, so that you can define packing number by dividing this volume with the entanglement volume. So this is the volume of an entanglement strand. So it is very interesting to see the value for different polymers so that you can measure the modulus, calculate the entanglement molecular mass, and then you can calculate NE for melt, B, A. And then in the end, whatever the flexible polymers tested, roughly this packing number is about 20. Okay, so that in the volume of confinement, A cube, you have 20 chains. Okay, and then there are certain effect of entanglement below that. So we don't know why this is so uniform. The value of NE varies a lot here between 7 to 81. And the volume changes a factor of 3 roughly, but the number of chains it's always constant. Yes?
Can you repeat again what's the entanglement parameter?
Yes. Okay, so then you, in a given chain emphasized here, so it's confined in a tube by entanglement with other chains, so that its size is roughly A. Okay, so that the chain can move in this distance, but not.
Okay, there can be multiple chains.
And in this tube, there is not only one chain, in fact. There are other chains. Okay, the blob is space filling, in fact, so that between blob it repels, but the chain can be inside. Okay, so that the number of chain strand is about 20. Okay? Okay, any other questions? Okay, so then we need to characterize the concentration dependence of this tube diameter. So entanglement, it means the binary intermolecular contact. Okay, so two chains touch. Okay, so if we use mean field theory, so this means chains are distributed homogeneously. In that case, the probability of contact, so this is the number density of binary intermolecular contact, DBC, should be proportional to the concentration of these two components, okay, to think in contact, so that probability is proportional to the product of concentration. However, experimentally, we have much stronger dependence by osmotic pressure, for example. In fact, mean field prediction, this means you distribute monomer chain homogeneously, but in reality, the real chain in a good solvent, the conformation changes. Okay, size also shrinks, and then the conformation is not constant. So that this mean field theory cannot, that is not take into account of this effect. So in this situation, it is found that this number density of binary intermolecular contact is inversely proportional to the correlation volume. So that this is the blob size. In that case, we can find the exponent here 2.3. Okay, this is a little bit stronger than 2. This means, in that case, the tube diameter it should be inversely proportional to the cube root of this density of contact. So it is, in fact, Guzai. So this is proportionality, so that we can simply use the tube diameter of the melt and add this concentration dependence of Guzai to have this relationship. Okay, so that A is in fact proportional to Guzai. This is B times phi 2 minus nu divided by 3 nu minus 1, and with this factor. Yes?
What do you mean by the distance between the things? Do you mean like 1, 2 has 2 other tubes, the distance between those, or what distance?
This distance. Which distance?
Well, it says the distance between binary molecular contacts.
Yes, so that when two chains are in contact, so this works as a topological constraint, so that this is an entanglement.
Well, if they're in contact, there's no distance between, or do you mean distance with, considering that's still a contact? I don't know.
Yeah, two chains are in contact, so that this gives you the entanglement.
So I would just presume the distance in contact would be 0,
Mm-hmm.
but this is not 0, so what do you mean by additional?
So here we need to know the probability to have this contact in space, so that this is the number density of this contact, and then it will give you the distance between these contact, so that it should be proportional to the correlation length.
Well,
In
is this the distance between separate contacts in space, like 2 different contacts?
I'm not sure of understanding what you...
Maybe I should just ask you after.
Yeah, yeah. Okay, so anyway, important thing is in a thermal solvent, this tube diameter is proportional to the correlation length Guzai, and there is a factor of root of NE, number of monomers in an entanglement strand. Okay? So this means here this is the relation for an thermal solvent. We know the concentration dependence of Guzai and chain size R also, so that we can extend this schematics of the length as a function of concentration to semi-dilute entangled regime. Okay, so the dependence is the same as in unentangled regime because topological constraint does not affect the chain dynamics at shorter length scale than A, so that we know the A here, so that from this concentration of entanglement, tau E, we start to have this entanglement tube size here, okay? And then the relation, in a case of a thermal solvent, concentration dependence is the same because A is proportional to Guzai, and the difference here, the factor is NE1 and its root, okay? So this is for a thermal solvent case. So in a theta solvent, in fact, mean field prediction works because in a theta solvent, chain conformation does not change, okay? So that it's, the chain size is always the same, independent of the concentration, so that we can say that this number density of binary intermolecular contact is simply just phi square. So this gives you different concentration dependent from the case of a thermal solvent, so that A is proportional to phi 2 minus 2/3. And then again, we can use A1 for the melt to use NE1 for the melt to have dependence. So that just to remember that phi is a function, Guzai is has its concentration dependence here, and then if we put 0.5 as nu, you have Guzai is proportional to phi 2 minus 1, okay, so that you have different dependence. Okay, so this complicates situations a lot. It's okay? Okay, so then we can determine the entanglement concentration where you start to have entanglement and you can start to define tube diameter. So that this is the concentration that this tube diameter equals the coil size. You know their concentration dependence here, so that this is A and this is R in a case of a thermal solvent. So that we can calculate phi E as a function of NE1 and N. And again, N can be replaced by phi star overlap concentration to find this relatively simple relation in the thermal solvent limit. In a theta solvent, however, A and Guzai have different concentration dependence, so that it's a little bit more complex. You can have A equal R. You have this relation, but you cannot eliminate N even if you use phi star. Anyway, whatever the solvent quality, when you see the N dependence, for a thermal solvent, it's N to 0.76, and for theta solvent, is N to 0.75. So practically, it's the same. But when you normalize it with the theta phi, dependence is very much different. Okay. And so this is plateau modulus. Okay, so this entanglement strand in the tube A, this is a Rouse chain, in fact, random walk of correlation block. So that again, this relation for Rouse size is the product of monomer size and its number with a root. We know the dependence of these parameters G and A also and phi, so that we can write NE phi as a function of G to have the relationship to have its concentration dependence. So this means it's important to understand that occupied volume of an entanglement strand, it's not A cube, because in A cube there are many chains, so that the volume is A square Guzai, okay? So that the plateau modulus is the energy kT per volume A square Guzai to have this relationship for an thermal solvent exponent phi to 3 nu divided by 3 nu minus 1, and for an theta solvent phi to 7 divided by 3. So again, this concentration dependence is practically the same, phi to 2.3 roughly. So this relationship, I think you saw often for if you work on hydrogels or other elastic systems. Okay, yes?
I don't understand what you mean by the volume of an entanglement. Is
So what carries the elasticity? This is an entanglement strand. So that this one strand, yes, part of the chain between two entanglement points. So it carries the elasticity. So that it has the energy kT. Okay, so that the modulus you can calculate each time if you need to have good accurate volume for that. For the strand, this is calculated as a square guzai. Okay?
So it's between entanglements.
Between
At the
entanglements.
entanglement point.
So this is the volume per entanglement strand. So that this is so this means this is smaller than a cube. In fact, you have the distance between two entanglement A, but in this volume A cube there are 20 chains. In fact, so that for volume the volume per strand elastically active, it's a little bit smaller than that. Okay, so that this gives you this difference. Okay, it's clear. Okay. Other questions? It's okay.
Is psi squiggle always smaller than A?
Yes. A is proportional to guzai, but it's always larger than guzai. Okay, so that and the difference is the root of NE, so that you can have the idea of the value. It depends on the flexibility and the size of monomers. Okay, so that it's relatively largely varying, so that tens of monomers per entanglement strand. Okay. And for the relaxation times, topological constraints do not influence the polymer motion on length scale smaller than the size of entanglement strand. So that entangled or even cross-linked, it's the same. So that you can use always the relaxation time of a correlation blob. We saw it for unentangled solution, so that this is the same. So that this is Jim relaxation time for the size of blob guzai. Okay. This means you have a concentration dependence. It's exponent of -2.3 for an thermal solvent and -3 for theta solvent. This is the same as what I previously shown. And then this is relaxation time on an entanglement strand, tau E, so that this is entanglement strand is a Rouse chain, it's a Gaussian chain, and then the monomer is blob, and its number is Ne over G. So this is the number of monomer in an entanglement strand. G is number of monomer in a blob. Okay. So that this is a Rouse time expression. Rouse time is the product of relaxation time of monomer. Here it's a blob, and then its size square. So we know tau guzai on the previous page, and we know its dependence in E over G. To have this dependence, and then we need to further check the concentration dependence of A. In an thermal solvent, it's proportional to guzai, but not in theta solvent, so that you see two different cases. In a thermal solvent, this concentration dependence is exponent of -2.3, same as that of relaxation time of correlation blob. But for a theta solvent, it's a little bit weaker. Okay, so we don't have the same concentration dependence. And then this is repetition time So that in the tube, this curved linear motion, so in the tube it's curved, but chain is a 1D diffusion, in fact, so that you have the diffusion coefficient, Rouse diffusion coefficient of the chain. So that repetition time is this tube length previously calculated, and this diffusion coefficient of Rouse mode. Professor Koibi showed that, so that this is kT over n zeta. This is the friction, so that each monomer feels the friction, so that you need n here. And tube length is here. I saw that for the melt, but basically it's the same. This is the case for melt. You can use it here, Ne phi. And then we calculate this, and this we can rewrite it this way. And this latter part is in fact sorry. This part is in fact equivalent to the entanglement time. So entanglement time, this is Rouse time, so that you can use this relationship for Rouse time. So this is the diffusion of object of size R here, so that you have zeta, and then this is the size. So here you know that the number of monomer in the strand is Ne, so that you can simply replace that, so that we can write in this simple relationship, tau repetition is the product of tau E, relaxation time of entanglement, with this curve dependence of n over Ne. And then we know how it depends on the concentration, so that we can summarize these to have these relations, so that basically it depends on the size, number of monomers in the chain, dependence of 3, and then concentration dependence, depending on the quality of solvent. So we can use this repetition time to calculate the diffusion coefficient, so that the diffusion coefficient of this repetition is the diffusion of the chain of its size R over the time scale of tau repetition, so that we can calculate concentration dependence for a thermal solvent and for a theta solvent to have different concentration dependence. So that I show you the same graph. We saw this for an entanglement solution, and here this is the entanglement semi-dilute part, so that basically it should scale as minus 1.85. Okay, so that depending on the concentration, diffusion coefficient show different concentration dependence. Okay, I need to accelerate a little bit. So this is the viscosity polymer contribution to the solution viscosity. This is product of modulus, entanglement modulus, and repetition time to calculate the terminal viscosity of this polymer. And then we can use different concentration dependence. And you have N, but N can be eliminated, replaced by the overlap concentration for the case of say, a thermal solvent. However, for the case of a theta solvent, you cannot replace fully, so that you have always N. Okay, so that this polymer size dependence of theta solvent. To normalize things, you need to have you need to know also the molecular weight. The concentration dependence of the specific viscosity for good solvent and theta solvent. So this is what you expect. But here for different molecular weight, for a good solvent, it does not depend on N anymore if you use phi stir. But for the case of theta solvent, you need to include this N dependence here. Okay, so the specific viscosity is normalized by N to 2/3 here. So then after that, for the specific viscosity, you have a different concentration dependence for dilute solution, semidilute, unentangled solution, semidilute, entangled solution for theta solvent and a thermal solvent. Okay, to summarize everything, in the entangled solutions, you have 4 different length scale, monomer size B, correlation length xi, tube diameter A, and chain size R. For each, you can have a characteristic relaxation time, modulus, and viscosity. I didn't show you these viscosity, but basically viscosity, you can, specific viscosity is the product of modulus and relaxation time divided by solution viscosity. We will use that later. And we have also the relaxation modulus for different time scale. So different relaxation time, tau 0 for monomer B, tau xi for correlation length xi, tau E for entanglement diameter, tube diameter A, and repetition time for the chain size. And you have Jim relaxation modulus below the correlation length scale or below the relaxation time of the blob. And above you have Rouse mode, and then you have elastic plateau. It's independent of the time, so that we can have a schematics of relaxation modulus with this 4 steps. At short time, you have Jim mode with a slope of minus 0.57 for a thermal solvent, and then you have Rouse mode, elastic plateau, and then it flows. Okay, so experimentally, how we can measure this? So that already the slope change is very, very small, so that is it possible to do that experimentally, accurately. And we can check the time scale of this relaxation time of correlation length, so that for monomer relaxation time, for flexible polymers, the Kuhn length is roughly the order of 1 nanometer. Solution viscosity is in the order of 1 millipascal second. If you work at 25 degree, KT is 4.1 to 10 to minus 21 joule, so that you can calculate monomer relaxation time in the order of 10 to minus 10 seconds. And then for the relaxation time of the blob, you add this concentration dependence to have this relation. So this is volume fraction 1 melt, you have this monomer relaxation time. It rapidly increases, however, still it's very small. For 1%, roughly, it's 10 to minus 5 seconds, 10 milliseconds. So that is it possible to measure that rheologically. So this is the question. For that, we try to measure by microrheology to go to the high frequency range. Okay, so at the next lesson, lecture, I will show that. Okay, so this is the end of the first part for semi-dilute solution dynamics, if you have questions. Otherwise, I quickly show the technique of microrheology by dynamic light scattering. I still have 15 minutes, roughly. Okay. Yep. Okay, so then we can use the technique of passive microrheology. Passive means just you use the thermal energy KT to measure the displacement of Brownian particles so that you can have movement of particles in viscoelastic media that you want to study. So that you need to measure the mean square displacement of your probe, and you should know the size. And the passive means just only thermal energy, and active you can apply externally the force. Optical tweezer or magnetic force or other force can be used. So I only talk about passive microrheology. So you can use the normal Stokes-Einstein relation. You saw that already. So that diffusion mean square displacement equal 6 dt for 3D diffusion. And then this is can be written in this format, KT divided by pi at solvent and the size of the object. And you have also time here. So this is the combination of Einstein relation and Stokes relation. So Professor Colby has shown it. So if you know the size of object, your probe, you can measure the viscosity, or if you know the viscosity of the medium, you can measure the size. So usually you do the dynamic light scattering to determine the size as you know the viscosity of your medium. It can be further generalized. Generalized means this Newtonian viscosity can be replaced by complex viscosity of your viscoelastic medium. To do that, you need to have one-sided Fourier transform, and then time should be converted into frequency, so that, but it's not necessary to go into very much in detail, so that this mean square displacement is the function of, again, the radius R, frequency, and complex modulus. Okay, this way, technically, you can measure, calculate the complex viscosity if you measure the mean square displacement as a function of time. So this, I think I can keep that. So that using one-sided Fourier transform, this means you need the data of mean square displacement, ideally from time 0 to infinite. But of course, you don't have for both limit, so that there are different simplified way proposed, so that the easiest is replacing Fourier transform by gamma function, so that Fourier transform, you have this integral part, so that you can use this gamma function. Gamma function is very complex depending on the value of G, but what we need is, in fact, the local slope of MSD as a function of time, if you plot it in log scale. And for passive microrheology, this slope is between 0 and 1, so that the gamma function between 1 and 2, this is relatively simple, so that it can give a relatively accurate estimation. Yes? Sorry? Excuse me?
So the alpha parameter is related to...
Alpha is the local slope of mean square displacement. So this means experimentally you can have these types of mean square displacement as a function of time. So you take the log of that and log of time. And then the slope changes locally depending on the time scale, so that you need to calculate this slope. Okay, so in the case of purely viscous medium, then you have the slope of 1, alpha equal 1, for whole time range, so that this gives you gamma function 2 is 1. And then this complex viscosity is viscosity equal viscosity multiplied by omega. And then here you have 1, and MSD should be 6 dt. Okay, so this way you can find d equal kt over 6 pi eta r. So that this is the normal Stokes-Einstein relation. Okay. The opposite limit is elastic matter. So if you do the microrheology of hydrogen at short time scale, of course it's moving, but particles are elastically trapped in the network so that it cannot go further from certain displacement, delta cube, as the value of MSD. Okay, so in that case, MSD is time independent, delta cube, and then the slope is 0, alpha equals 0, so that gamma function should give 1, so that we input that to have complex modulus is time independent, and the value can be determined from this delta cube. Okay? And in between, you have viscoelastic solution that we are interested in, and then the slope is changing between 0 and 1, depending on the time scale. So that in that case, you need to calculate this slope alpha as a function of frequency. Okay? Okay, experimentally, you can use dynamic light scattering, you can use particle tracking, so you can use CCD camera and a microscope to detect. But we want to go to high frequency ranges so that we use the technique of light scattering. I think you have access to commercial dynamic light scattering apparatus, and then you can do microrheology. Of course, there are some small details which can be very carefully done, so that you can use goniometer system or fixed angle system. There are commercial products also nowadays. Okay, so for single light scattering, you pass the laser and scattering angle theta here, and then you detect the scattered light intensity as a function of time to calculate its autocorrelation function. So if you did particle sizing by DLS, you should know that. Scattering vector Q for dynamic light scattering is the same here. You have only wavelength of laser lambda, which has the unity, so that Q is the unit of 1 minus meter. Okay, so that 1 over Q gives you the length scale, as Professor Bourret explained this morning. We can use the technique of diffusing wave spectroscopy. So this means you put probe particle a lot, and then the photon makes the multiple scattering. So it's a random walk of the photon, so that statistically you can have an averaged value and the small displacement of each particles are accumulated, so that you can have better resolution, as I go to show you. So the parameter, important parameter at the length scale is this L star transport mean free path. So this means when the photon penetrates into this distance, L star, the photon loses its initial orientation. So that this means it's multiple scattering. If it's single scattering, this L star is much longer than the size of sample, so that the scattering event occurs only once. On the contrary, if this L star is much smaller than the sample size L, you have multiple scattering. So this means you want to see through the sample because sample is very turbid because of scattering of the from the particles. Theoretically, this ratio should be 20 or more, but experimentally we found that 10 or even 5 works reasonably well, so that there should be certain simplification of equation, but that's what we found. So that typically I try to do that with 20, but sometimes it's less. Yes?
It's just the probe particle which are scattering and not the polymer.
You disperse probe particle in your polymer solution that you want to characterize.
So the scattering will just be by the probe particle.
Probe particle, exactly. So I will show you about that also. So once you have autocorrelation function, then you can convert it into mean square displacement. For DLS, single scattering, it's very simple. Just you need to know the scattering vector Q. And for DWS, it's much more complex. We don't need to go into the detail, but you have mean square displacement and L star. And K0, it has the information of the wavelength, like Q. Okay? So that this equation we need to resolve numerically, but it's possible. Okay, for a probe particle in water, so that mean square displacement should be theoretically proportional to time with the slope of factor of 6d. This is a theoretical line. So if you do the DLS measurement from autocorrelation function, you can calculate easily this mean square displacement. You can change the scattering angle to have several curves which should superpose, and then the range is slightly different because of this Q square dependence. You cannot go, however, very low value, so that this is a sine of theta over 2, so that if you even go to 180 degree, you cannot go very further. However, for smaller angle, you can go as much as you want if you set up small angle light scattering setup. So the advantage of multiple scattering, DWS, you have multiple scattering events so that it's more sensitive to the small deformation. So the mean square displacement is in the, as nanometer square. It can be order of 1 nanometer square, so that you can detect the displacement roughly in the order of nanometer. At the next lecture, I will explain what it is, but this is just polymer solution with very viscoelastic, high molecular weight polysaccharide, so that we can compare DLS and DWS, and then I have no adjustable parameters, but you can cover very wide range of time and MSD. So roughly DLS cover this MSD value range, and DWS is a little bit lower. So this means if you increase the polymer concentration, displacement is much lower, so that with DLS, it's hard to detect. But DWS, it can be possible. So that this is the root of mean square displacement to have an idea of the displacement. So the probe size is 1 micron, so that here it corresponds to 1 micron. So that you may have the image of particle moving like that, but everything is very at short time, so that in fact, particle does not move even, or if the displacement is much smaller than its own size, okay? But it's enough to detect elastic cage and flow for most of cases. And we can compare microrheological techniques and classical shear microrheology. So the macrorheology data were taken by Guillain, so that you can see these data point of macrorheology, and then all these colored curves from microrheology, and then it superposes reasonably well for this system, and then it can cover, let's say, 10 to minus 2 Pascal, but it's getting less accurate. At higher modulus, it can be thousands of Pascal. 10 kilopascal, it's very difficult already, as we use only the thermal energy KT. When the system is elastic, then displacement can be too short to detect even with DWS. Okay, so we can check the accuracy of the validity of the technique by comparing with macrorheology. Okay, if you want to use the DLS apparatus to do the microrheology, as you asked, so in the system you have your polymers, and then you put probes, but both scatters, right? So that you need to have very good contrast between them, so that scattered light from probe should be much higher than the polymer. So this is not very much easy often. So if you work on water, adjusting the index, it's not very much possible often, so that you can try, but I have never succeeded. size dependence here. What I don't understand is that this value, I expect something faster, but it's always lower. So that for DWS, also L star value changes, so that there should be certain complication here. Okay, this is one of the last data publication of David White, who started DWS, and after that he finished. He showed for the solution of PEO in water, different probe size, and then it's superposing well. So this is one way to check if you have a good probe size. Okay, he tested between, let's say, 0.5 to 2 microns. So this is typical range. If it's smaller, it's not easy to have multiple scattering. DLS, it works. If it's too big in water, it's sedimentate. Okay, so that 3 micron is almost the limit. And this is the last slide, so that you need to be careful with the surface chemistry of probe, so that these particles should be stably dispersed in water or as a medium, so that you need to have a good chemistry of that with the affinity of the solvent and not to have the interaction with the polymer. So that in the same paper of David White, he compared sulfate modified polystyrene and carboxylated polystyrene, so that this is reasonably close. So this is what he said. Otherwise, if you have strong interaction, most of cases you see it immediately because it can phase separate. And the scattering rate intensity can strongly depend on the concentration, so that there are different ways to check that. Okay, I have to stop now, so that so at the next lecture, I will show you 3 examples, and then first example about the correlation length. I showed you what is the problem at high frequency regime, so that I try to measure correlation length. And then there are 2 examples, and of course there are theoretical part to better explain, because at higher frequency, theoretical works are more abundant than the experiment. Okay, thank you very much.